Hello everyone, welcome to Chapter 17, Section 3. We're going to take a look at titrations of strong acids with weak bases and weak acids with strong bases. But we're also going to take a look at why the equivalency point does not have a pH of 7 when you do those type of titrations. And of course, another thing that we're going to check out is how to get the pH along any point of the titration curve. Maybe not necessarily the equivalence point, but any point along the way. All right, so let's begin. Make sure you have your guided notes and a calculator.
A traditional titration that you guys have done before is with a strong acid and a strong base like HCl and NaOH. That would be the typical one. So for these guys, they're showing you the various different points along the titration. And right here you've got the remaining acid. You got the acid still trying to be neutralized. But at the equivalence point, this is when you've got salt with the the salt and the water, because basically that's what happens is you react an acid with a base and you usually get salt. But that's only true with a strong acid and a strong base. Sometimes the salt that's produced, as you've now discovered, sometimes the salt that's produced can have a pH. So not all salts are neutral. So for example, sodium carbonate will not produce a neutral solution because of the carbonate ion. The carbonate ion messes around with the water. It hydrolyzes. All right, and then the last part of it, more bases added, and so the pH would increase. All right. Here is a titration of a weak acid with a strong base. So you need to think about the weaker link. Who's the weakest link in this particular titration? And that would be the acid. And since the acid is so poor and it's so weak, look at the equivalence point. It's no longer sitting around at 7. It's a little high. Okay, it's a little high. It's a little bit in the base area. And so that's how I think about it. I think about, okay, in a titration where you've got one weak partner, who's the weakest link? And whoever the weakest link is, they are not pulling their load. They're not pulling their fair share. So this acid is not pulling his fair share, and so the equilibrium or the titration here will flip up a little bit, will shift up a little bit over 7 into the base territory. Okay? Alright. And the equivalence pH is greater than 7. Okay. Moving on. Phenolphthalein is commonly used for these titrations. Yes, and you guys used phenolphthalein today. So perfect. Alright, so titration of a weak acid with a strong base. They are sitting here talking about how you would be able to figure out the equivalence point. It says, at each point below the equivalence point, the pH of the solution during titration is determined from the amounts of acid and its conjugate base present at a particular time. So you know that you're probably going to be working with these ice tables more. Alright? So anytime you have a titration where you have one weak partner, whether that be a weak acid or a weak base, you know you're probably going to have to be doing some ice tables, okay? If they're asking you for a pH, they basically are asking you to do an ice table, okay? Alright, titration of a weak acid with a strong base. Here are some Ka values and where you can expect their equivalence point to be. So these are all weak acids with a strong base, and you can pretty much check this out, and it's really cool because you guys all think that titration should end at, a pH of 7. That's not the case, okay? So depending on the Ka value, your equivalence point could be very, very different, okay? Moving on. Titration of a weak base. So now we're switching gears. We were talking about a weak acid. Now we're going to talk about a weak base. And so it's just the opposite. Like, who's the weakest link? The base. The base is not able to pull his fair share. So the equivalence point is going to shift into the acid territory. Okay, the acid is the stronger guy, so it makes sense that the equivalence point would be shifted towards the acid. And for these type of titrations, methyl red is what we like to use. And so I've got a lot of methyl red phenolphthalein indicator in my cabinet. And those are the two that are preferred for these type of titrations, okay? And then they end the section with a review of polyprotic acids. So remember how a polyprotic acid basically has more than one hydrogen. And every time you lose a hydrogen, you have that famous little, straight up and down curve basically on the pH scale, which is kind of neat. So in this particular case, they are titrating phosphoric acid with some kind of base. And each time it loses one of its hydrogens, because you have to neutralize each hydrogen on the polyprotic acid. So every time you lose a hydrogen, you will have this straight line, and so this would correspond with the pKa 1, and this would respond with the pKa 2. So it's kind of cool there. Alright, this is the next section, so I'm done with the lecture, but what I want to do is show you a few examples. Okay, so now we're going to check out sample exercise 17.6. This starts on the bottom of page 731. Alright, calculating pH for a strong acid, strong base titration. It says calculate the pH when the following quantities of 0.1 molar NaOH solution have been added to 50 milliliters of 0.1 molar HCl solution, and A at 49.0 ml, and then B at 51 ml. Alright, so you need to keep in mind that basically all this is a neutralization reaction. You've got a really nice strong acid and a really nice strong base, so we don't really have to worry about our Ka values or Kb values or anything like that, okay? This is very simple and straightforward. What we need to do is to calculate the number of moles of acid present at each of the volumes. So remember, it's all about the mole-mole cancellation. It's all just basically stoichiometry. So what we're going to do is we're going to take, for part A, right, we are going to take the quantities that they gave us. We've got 0.100 molar NaOH, and then we've got, let's see, we're always working with the 50.0 ml of 0.100 molar HCl. Alright, for part A, the quantity of this guy is 49.0 ml. And so we got to figure out if there's anything left over, and if there is, what the concentration would be. Okay? Alright, pretty straightforward. So the first thing I'm going to do is I'm going to work with this guy to figure out the number of moles present of the acid. So it's pretty simple. You're just going to take the 0.100 molar and then multiply this by 0.050 liters. That's what 50 milliliters is. And you should get, let's see, that should be 5.00 times 10 to the negative 3 moles of acid. So we're going to just, it's a strong acid, so we know that we can put H plus on that one. Alright, so we need to do the same thing with this quantity now. So we're going to take the 0.100 molar and multiply it by 0.049 liters. And let's see, you should get 4.9 times 10 to the negative 3 moles of OH ion. Okay, so for any kind of titration thing, you are more than welcome to do an ice table. Ice tables work really good for titrations, and so basically you've got an acid and you've got a base, right, and it neutralizes, I'm going to put a full arrow here, into forming water. Okay, initial change equilibrium. Okay, alright, your initial on your H is 5.0 O times 10 to the negative 3, and we're going to assume nothing on the base yet, and that's basically what we're adding as the base. So basically what you need to think about is that in the OH is going to be neutralizing with the H+. So back over here, you are adding 4.90 times 10 to the negative 3 moles of your base, okay? That's going to be completely fully consumed by the H+. So all of this is going to be gone. There should be none left when this neutralization is done for your OH. But the question is, how much is left here, right? Because it doesn't look like all of it was used up. So you're going to take 5e negative 3 and subtract 4.9e negative 3. Right, you should get, for this, when you subtract, 1.00 times 10 to the negative 4 moles of H+. Remember, I'm using moles, not molarity, for this particular ice table. All right, and the final step is to figure out what the total volume of the solution is at that point. So remember, you got 50 milliliters of the HCl, and you added 49 milliliters of the base. So the total volume is 50 plus 49. You've got 99 milliliters. So you know what you have to do, right? You need to take the number of moles you just got and divide it by, not 99 milliliters, but 0.099 liters. Okay, it's always liters. So let's go ahead and do that. 1e negative 4 divided by 0.099. And you get 1.01 times 10 to the negative 3 molar on your HCl. And so now all you have to do basically is do the negative log of that answer. So on your calculator, just keep rolling, go negative log of your answer, bam. And I get 2.995. Shoot, that's basically 3. 3.00 for your pH. That's what your pH is. And let me check the book. Yep, that's what the book said. Alright, so for part B, you're going to do pretty much the exact same thing that I just showed you. But this time you have slightly different quantities. Alright, so I'm gonna save the number of moles that I used in part A for your HCl. But now I need to make sure that I get the moles of NaOH correct because the volume changed. So it's 0.100 molar times 0.051 liters. I shouldn't need a calculator for this, but I'm cheating anyway. Alright, 5.1 times 10 to the negative 3 moles. Okay? So now, and this is OH. So now, when you do your ice table, it looks like we have more OH than we did in the last time, right? So it's going to be just a slight tad bit different. In the ice table, your H plus is going to start with the same as part A. This will be 5.00 times 10 to the negative 3. This guy is right here, it's 5.1 times 10 to the negative 3. Okay, this guy starts off with 0. And now, look at this. All of this is going to be gone. And you'll have a little bit of this guy left over, right? So, what is 5.1 E negative 3 minus 5e negative 3? It is 1 times 10 to the negative 4. And remember, this is moles, just like it was before. So we need to make sure that we do the total volume again. So the total volume is 50 plus 51. That's 101 mLs. 101 mLs total. So we're going to take the 1 times 10 to the negative 4 moles. And remember, this is OH, so be careful if you're asked to figure out what the pH is. Divided by 0.101 liters. So 1e negative 4 divided by 0.101. This is 9.9 times 10 to the negative 4 molar. And remember, this is OH. Concentration OH here. So be careful. We need to go through the whole pH wheel, if you will. Let's see, so negative log of this answer, so negative log of that will give you about 3. So your pOH is equal to 3, which means therefore that your pH, 14 minus 3, is 11. 11.0. Final answer. Alright. So strong acid, strong base titration examples are super easy. It's all about the stoichiometric values, and should be a pretty simple one for you guys to work through. Alright, so 17.6 example is pretty straightforward. Let's do the sample exercise 17.7, and that one starts on page 735 in your textbook, okay? So let me go through and find that. There it is, okay. Okay, sample exercise 17.7 says calculate the pH of the solution formed when 45 milliliters of 0.1 molar NaOH, that's a strong base, is added to 50 milliliters of 0.1 molar acetic acid. There's your weakest link is right there. So I'm going to make you predict right now. you have a strong base, a weak acid. The weak acid is not able to pull its load. So at the equivalence point, what would the pH be at the equivalence point? Would it be above 7 or below 7? That'll be one of the questions on your free response, okay? Or your guided notes. Alright, so let's tackle this problem. Obviously, we're going to want to start with the number of moles this time. So one of the first things I'm going to do is calculate the number of moles that are currently in this solution right here. So I'm going to take the 0.100 molar and multiply that by 0.0450 liters. And let's see, 0.1 times 0.045. Alright, so I get 4.5 times 10 to the negative 3, and that's moles. This is a strong base, so we can pretty much assume that that's all OH. Okay? So that was the easy part. The hard part comes from the acid. Okay, the acid is where you're going to run into a stumbling block. Alright, so you've got 50 milliliters of the 0.1 molar acetic acid, okay? One of the first things, since we're working with moles of OH, normally on an ice table we could use just molarity and stuff like that, but when you're in a titration and you're dealing with a specific volume of acid or base, it's more typical in your ice table to go with moles this time. Because as you add more of the solution, you're adding more moles, okay? Alright, so the concentration is 0.100 molar of the acetic acid, and you've got 50 milliliters, so 0.050 liters. And you're going to get 5.0 times 10 to the negative 3. And now you've got moles of your acetic acid. And this time, watch how I write it. I'm making sure that you realize that this is a weak acid and it's not going to ionize well. Up here, I was totally comfortable with putting OH. But down here, this is a weak acid. So we're not sure exactly how much H plus ions there are to neutralize in this particular guy. Alright, so when you set up your ice table, you need to realize that you've got this going on. CH3COOH. You got your acid. Your base is totally strong, nothing wrong with that. Alright, so check out your products. It'll be the typical products. CH3COO ion. And then of course you got your water. So we're hoping that that hydrogen pops off of that acetic acid. That's basically what we're trying to make happen here, okay? Alright, so ICE. Alright, the initial is before the combination, basically. Your book uses before addition, addition, and after addition. It's the same thing to me. It's all ice. Alright, so anyway, your acetic acid, we're going to use the moles here. This will be 5.0 times 10 to the negative 3, and remember this is moles, not molarity. Your OH, you had 4.5 times 10 to the negative 3 moles. Alright, so it looks like for us, if we count our cards right, you should have a little bit of this guy left over, right? The 0.50 times 10 to the negative 3 moles of this should be left over. And therefore, on your salt, like water, we can't really do a concentration on. But over here, you should have 4.5 times 10 to the negative 3 moles. Oops, sorry, my screen is popping out there. There you go. Moles of the anion. Okay. Alright, so this is the start. And basically what you are worried about is the fact that not all of this weak acid is gone after the addition has been made. And that's concerning to us, right? But remember, this is a weak acid, right? So one of the things that we should probably do is figure out the total volume, 45 plus 50, to figure out the total volume of the solution. And obviously that's 95.0 mLs. Alright, so that's pretty easy. Now on to the to these guys right here. Right here and right here. We are going to go ahead and figure out, because remember, you got an acid and you got a conjugate, its conjugate base. And anytime you have an acid with its conjugate base, guess what you've got? You've got a buffer. Alright, so let's go ahead. We got our final volume here. Let's get the molarity of these dudes. Okay. Give myself a little room. Alright. So we've got 0.5 times 10 to the negative 3 moles of the acetic acid. So I'm going to go HA, just generic. And the volume is 0.0950 liters. That's up here. So that'll give us the concentration of the acetic acid. And then you got this guy, 4.5 times 10 to the negative 3 moles. And this is your CH3COO. There's your conjugate base over 0.0950 liters. Alright, let's do our math here. Let's see, this guy's going to be 0.0053 molar. This guy's going to be 0.0474 molar. Okay, so here we go. Basically what you got is you have the acid and the conjugate base. So one of the great things that we can do here is the Henderson-Hasselbalch, however you guys want to pronounce it. It's not, what did you guys say? Hasselhoff? It's not the Hasselhoff equation, okay? Alright, but anyway. So the Ka value for the acetic acid was given to you in the problem. That's very nice. It was 1.8 times 10 to the negative 5. What we need to do is figure out what the pKa of this guy is. So you can do the negative log of that. So negative log 1.8 e negative 5. pKa is then therefore 4.74. Right? This is your pKa. Okay. So pH, right? Is that the whole point of this problem? They want to know the pH? Yeah. Okay. So pH is equal to pKa plus the log of the base over the acid. Okay, that's the formula, okay? The pKa that I just got was 4.74 log. Your base is the salt, this guy right here. So you got 0.0474 over your acid, which was right here, 0.0053. Alright, so let's check to see if we can correctly solve for the pH given all of the stuff that we just got there, okay? Alright, so let's see, log, open parentheses, 0.0474 divided by 0.0053, close the parentheses up, and we're going to add that to 4.74, bam! I get, final answer, 5.69. Right, I really hope that that's right. Woohoo! It says that it's 5.70. Score. Alright guys, we win. That is the basics on how to do the pH for a weak acid, strong base, or even a weak base, strong acid titration, okay? Basically what you got to do is, it's not really an ICE table, it's more of a stoichiometric ratio to figure out what's left over after the addition. In this case, we had a little bit of the weak acid left over with its conjugate base, and so we knew that we had kind of a buffer thing going on. So we went ahead and did the Henderson-Hasselbalch equation, and bammo, got our pH. Alright. Let's see, the other sample exercise is 17.8, calculating the pH at the equivalence point. I'll do that real quick for you. Oop. So, oop, you don't need to see everyone's grade. Sorry about that. Okay. Continue. Let's see, 17.8. Here we go. Front slide. Alright. 17.8 starts on the bottom of page 735. Here we go. I said here we go. Oh. There we go. Okay. It says calculate the pH at the equivalence point in the titration of 50 milliliters of 0.1 molar acetic acid with 0.1 molar NaOH. So you have no quantities this time, but one of the things you do know is that the equivalence point, the mole ratio between your acid and your base will be exactly the same. So whatever moles we get for the acetic acid will be the same number of moles for your sodium hydroxide. Alright, so that's the way we're going to tackle this problem. First thing I'm going to do is go ahead and figure out what this is. The 0.100 molar times the 0.050 liters for the acetic acid 0.1 times 0.05, bammo. You get 5 times 10 to the negative 3 moles. And this is a weak acid, so I'm not going to change the formula. Alright? Okay, but we know that the number of moles of NaOH should be the same at the equivalence point. So guess what this also is equal to? This is also equal to the number of moles of NaOH. Okay? Alright, because that's the equivalence point. So, let's see, I'm flipping the page to 736 just to triple check the way that I tackled this problem. Yeah, we're looking good. Okay, so the way that they also said this is that if you think about the chemical reaction itself, the CH3COOH plus the, basically it's just the hydroxide that we're all worried about, what you'll get is CH3COO negative and your water. Okay? So one of the things that they want to remind you of is that if you started the reaction here with 5 times 10 to the negative 3 of this, 5 times 10 to the negative 3 of that, guess what you're also making that also has a number of moles of 5 times 10 to the negative 3? You guessed it. You're making, so this is all gone, this is all gone. You're making 5 times 10 to the negative 3 moles of the acetate ion. Okay? So guess what we're worried about with the acetate ion? And remember how I told you this before? When you've got a weak conjugate of anything, okay, conjugate acid or a weak conjugate base, you always have to worry about how that guy is going to react with water. Remember the hydrolysis process. So you got an ion that is going to interact with the water that is in the solution. Okay? So basically what we're now worried about, like I just showed you what the titration would look like, but this is what we're worried about. We're worried about this ion doing this. Going back, right? To make the acid. Okay, this is what we're kind of worried about. So this ion is weak, and guess what I'm going to make you guys try to find? What we need to do is figure out what the K sub B is for this dude right here, because it's acting, it's going to be making, right? It's going to be making a basic solution. So we need the K sub B for that ion. This is just like the common ion effect that we learned previously, okay? Alright, but anyway, it can be calculated from the Ka value of this guy. So if you know the Ka value, which you do, of acetic acid, then we can work back to figure out the Kb. So the Ka value for this guy is, from the previous problem, 1.8 times 10 to the negative 5. So then to figure out the Kb, you would take Kw and divide it by Ka, and I'll save you the heartbreak of doing this. Your Kb value should be 5.6 times 10 to the negative 10th. Alright. So what would the Kb value look like for this particular reaction, okay? That's the next question I got to make sure we get. Okay, hold on. Boop, boop, boop. Okay, so Kb, oops, sorry, hold on. Right, so Kb will look like the acid. So CH3, look at your products, COOH. Okay, we need the concentration of this guy. We need the OH ion concentration. And then you've got the CH3COO ion. Okay? The good news is that we know that this guy, from the reaction, we know that this guy should be 0.0500. The problem is that we don't know how much we lost. If you think of an ice table, this guy lost a certain amount, right? It did react a little bit with water, so a little bit of it did go away. We don't know these concentrations. They're X and X. Alright, so what we have basically is X squared over 0.0500 minus X. And that's all equal to 5.6 times 10 to the negative 10th. So here's our situation. Alright guys, you remember how whether or not you can ignore x? Okay, you're going to take this value, put it over, let's see, over or under? Oh gosh, I can't think okay, 5.6 times 10 to the negative 10 divided by 0.0500, times it by 100 and see what the percent is. Remember, if it's 5% or higher, then you need to do your quadratic. Okay? But luckily for us, it is way less than even 1%, which is nice. So all we're going to have to do is to say get rid of this. And so basically you have x squared is equal to, I'm going to do the math, 0.05 times 5.6 e negative 10, figure out what the answer is, and then take the square root of that. Square root, answer, bam. Alright, looks like x is equal to 5.29 times 10 to the negative 6, and guess what that is? That's your OH concentration. So be careful. They want you to get to the pH. So what I'm going to do is figure out POH. So I'm going to do negative log of that answer. So let's see, negative log answer, bam. I get 5.28-ish. And now to figure out pH, just take 14 minus that answer. 14 minus the answer. I get about 8.7-ish. Alright, let me check my answer. Woohoo! It says the answer is 8.72. I got 8.72 if you want to be technical. There you go. Yay! Alright guys, I am done with this podcast. I hope I didn't take too much of your time. I know the lab took some of you guys a considerable amount of time, and some of you guys actually did not clean your lab. So I'm expecting you guys to see you guys again Monday. I am not going to clean your stuff for you, and I'll catch you later, okay? Bye.